Hello, my name is Evan Wallace, President of Applied Physics. In this video, I'd like to demonstrate one of the most surprising facts in all of physics, that different gases largely ignore one another when they're all mixed together. This simple idea explains why compressed air can't keep champagne fizzy, why nitrogen gives Guinness Stout its creamy head, why scuba divers have to worry about the bends, and even how fish are able to breathe underwater. To understand how this works, we're going to look at gases from the molecular point of view, watching the behavior of individual molecules. This approach, known as kinetic theory in physics, provides a remarkably intuitive picture of how gases behave. To make these ideas visible, we built a molecular simulator, and that's where we're going to start. Consider this setup. I have an airtight chamber with two sides, a left and a right. There's a door between them that I can open and close by clicking this button, like so. And with these plus buttons over here, I can add two different types of molecules to the chamber. And for now, I'm just going to call them molecule A and molecule B. So now I'm going to add 40 of the molecule A, the red molecule, to the left side, to the left chamber. Let's try it. There's 10, 20, 30, 40. You can see the count of molecules down here. There's 10. 20, 30, 40, and you can see that the pressure of the gas is 80 pounds per square inch. Now I'm going to open the door, and I want you to notice that when I do that, molecules are going to travel from left to right, but it's not that the pressure of the molecules is forcing them from left to right per se. Rather, the molecules are just going about their business, traveling the path they're on. Sometimes they hit the open door, and sometimes they don't. Let's watch. You can see that the pressure is going down here and up here. And when the number and pressure of molecules is the same on the left and right, we get equilibrium. You can see it there, the two tiles colored in a pink color. Now note that at equilibrium, it's not that nothing is going on. There's a whole lot going on. There's lots of molecules going from left to right and lots going from right to left. But at equilibrium, those two processes are happening at the same rate. That's what we call equilibrium. Now, a reasonable question to ask is, can we add a pressurized gas on the right to keep gas A in place on the left? Say, for example, if we were to add 40 molecules of gas B on the right, will that keep the 40 molecules of gas A in place on the left? Let's try it out. Let's start the simulator over. We'll add 40 molecules of gas A on the left. There's 40. That shows 84 psi. And we'll add 40 molecules of gas B on the right. And it's, again, about the same pressure. So now we have 40 on each side. They're at about the same pressure. And let's open the door and see what happens. Well, that's interesting. The gas A is moving from left to right pretty much unimpeded, and gas B is moving from right to left pretty much unimpeded. Note that the pressure of gas A is falling over here and rising over here, and the pressure of gas B is falling over here and rising over here. And pretty soon, in short order, gas A comes to equilibrium. The two tiles light up, as you can see. And gas B is also tending towards equilibrium. And now the tiles light up, and those two gases are in equilibrium. So it's almost as if the two gases don't care about each other at all. They pass by one another without having an effect on one another. They both come to equilibrium. We use a term called partial pressure. Now, since we have two species of gas in the same container, note that gas A, the red molecules, are making up about half of the total pressure, and gas B, the blue molecules, are making up the other half of the total pressure. So each has a partial pressure of about 1/2 of the total pressure of approximately 90 psi. The principle we've just observed was first recognized by the English chemist and physicist Dalton, who lived in the late 18th century, early 19th century. Dalton realized that when several gases occupy the same container, each behaves almost as though the other were not present. Rather than responding to the total pressure of the mixture, each gas exerts its own partial pressure, or component pressure, and reaches its own equilibrium independently. Today, this idea is known as Dalton's law of partial pressures, and it has become one of the fundamental principles of chemistry and physics. And I think now you can see where we're going with this. If we were to give these molecules names, perhaps we'll call molecule A carbon dioxide, and we'll call molecule B argon. And we ask the question, if you were to pressurize the headspace of a champagne bottle with argon molecules, would that keep the CO2 molecules in solution? And I think you can see from this demonstration that the answer is no. You can only keep carbon dioxide in solution in champagne with a partial pressure of carbon dioxide that balances the concentration of CO2 in solution. Argon would do absolutely nothing. You could have 1,000 psi of argon in the headspace, and it wouldn't make one bit of difference as to the amount of CO2 that remained in solution in the champagne. We're going to explore this in more detail later, and I hope you'll join us.